Hello friends, welcome to my YouTube channel Scholars and Curious. And physics is obviously for curious ones, as I always say. This is our lecture series of solid state physics, and today we will discuss about band theory, and it is the part 1 for band theory. Basically, this video is for all 12th standard students doing graduation and appearing in all university MSc entrance exams, CSIR, NET, JRF, GAT, JEST, TIFR, BARC, PhD entrances, etc., etc. So yes, we'll start with the energy band theory, and you can see here a diagram this side, right side. So this is the distribution of electrons in shells and subshells. This is the nucleus. These are the shells. This is your first shell, second shell, and third shell. And the outermost shell like this one, the third one, the last one, has 4 electrons which are free to move. So those electrons are valence electrons basically. So all the band theory depends on these electrons, these valence electrons. When they will excite, they may go into conduction bands, and they may make any conductor. What are the conductors, insulators and semiconductors, and one by one we'll study each. So these are the 3 categories of solids, and these are based on their conducting properties like conductors, semiconductors and insulators. You guys know this thing. Now, here is a table. The table is electrical resistivity and conductivity of selected materials at the room temperature, like 293 Kelvin. So, let's observe one thing in this table. First one is silver metal. Silver is a metal. Okay, material is silver and it is a metal. You guys can see the resistivity is 1.59 into 10 to the power minus 8 ohm meter. It is too small. It is too small because the power is minus 8, 10 to the power minus 8. Now, let's see this conductivity of silver. It is 6.29 into 10 to the power 7 ohm inverse meter inverse. Conductivity is too high, very high. So, metals have resistivity low but conductivity high. Coming down, let's talk about alloys. Let's talk about nichrome. Nichrome has resistivity 1.5 into 10 to the power minus 6 ohm meter, but conductivity 6.7 into 10 to the power 5 ohm inverse meter inverse. We can again observe that resistivity is low but conductivity is high. This conductivity is relatively low to the metals, but it is also high, very high comparison to this resistivity. Let's come to the semiconductor and let us talk about germanium. Germanium, silicon and carbon. So germanium, it has the resistivity 0.46 ohm meter and the conductivity 2.2 ohm inverse meter inverse. Not much difference. That is why it is semiconductor. It may be insulator or may be conductor. And the last one are insulators. So let's take an example. Wood has the resistivity 10 to the power 8 to 10 to the power 11 ohm meter. It is too high. And the conductivity is 10 to the power minus 8 to 10 to the power minus 11 ohm inverse meter inverse, and is too low. That is why wood is an insulator. Okay. So what results we are getting by observing this table? So the table reveals that the electrical conductivity at room temperature is quite different for each of these 3 kinds of solids. Like now we know that metals and alloys have the highest conductivities, followed by semiconductors and then by insulators. What is the reason? Let's start talking about the reason, and the reason is band theory. So the band theory starts with the construction of an isolated atom. So this is an isolated atom and the electrons are arranged in their respective energy levels. These are the electrons. The red one In center is the nucleus. The nucleus have positive charge and the electrons have negative charge. Now, you guys can see that in the first shell, in the innermost shell, there are 2 electrons. And then in the second shell, there are 8 electrons. Okay. And in the last shell, the outermost shell, there are 2 electrons. According to this rule, we know how to fill the shells now. The rule is 2n square. According to this rule, in the third shell, how many electrons there should be? N equals to 3 if we are putting, so 3 3 is 9, 9 2 is 18. There should be 18 electrons in this shell now, but there are only 2 electrons. One is here and second one is here. There are only 2 electrons. So, these electrons are free to move. Okay. And these electrons contribute in the band theory. Now, if these electrons from valence band can excite in conduction band, then they make a conductor. They follow the property of conductor. Okay. Now, just look at this diagram, this graph in the left. Energy levels are, you can see the energy levels, increasing number of energy levels. This is energy level number 1, number 2, number 3, number 4 and number 5. Suppose the outermost electron is here in this energy level at number 1. And anyhow, it gets excited and reaches here. Now, if there are n atoms, then there are n types of energy levels overlapped each other and they may form a band. We'll understand it in next coming slides. So moving ahead. In solids, the outer electron energy levels become smeared out to form bands. Yes, you know this thing now. So look at this one. This is an insulator and there is a large band gap between valence band and conduction band. Now, what is valence band and what is conduction band? You will get to know in between this lecture. Basically, valence band is that which have some electrons and they, if anyhow they may excite and can conduct, then they may come here. So, it is a conduction band, relatively having high energy. Conduction band is about for conduction of electrical energy. And the second one is your semiconductor. It has comparatively low energy gap. And look at this conductor. Both conduction and valence bands are overlapped. Okay. So if there are some electrons in this valence band, basically the valence band is the highest occupied band, highest occupied by electrons or holes, we may say. For conductors, it is electrons, and for semiconductors, holes and electrons both. So the highest occupied band is called the valence band. This is full. And some electrons may come into this conduction band. If, look at this conductor one, if there is no energy gap, they may travel from here to here very easily. That is why conductors can conduct the electricity. Semiconductors have some energy band gap. That is why we have to excite some electrons from here to here. And insulators have the highest energy band gap. Okay, so these are the definitions. I think you know these things now. Let me read out. Insulators. There is a big energy gap between the valence and conduction band. Examples are plastics, paper, wood, etc. Conductors. There is an overlap between the valence and conduction band. Hence, electrons are free to move about. Examples are copper, lead, silver, etc. And semiconductors, there is a small energy gap between the two bands. thermal excitation is sufficient to move electrons from the valence to conduction band, and examples are silicon, germanium, etc. So, when a conductor is heated, its resistance increases. This graph is for a conductor. We are increasing the temperature. Resistance also increasing in conductors. Please make a note. This is the graph of a conductor. When we are increasing the temperature of a conductor, the resistance also increases. That means, what does that mean? That means if resistance is increasing, the conductivity is decreasing. If the conductivity is decreasing, that means it is going to be less conductivity for electricity. Yes, it is not, so it's not good for a conductor. Like if we are increasing temperature, the conductor slowly loses its virtue to conduct electrons. Okay, and here in the right side, the graph between R and T is of a semiconductor. So in a semiconductor, when we are increasing the temperature, the resistance starts decreasing. These two phenomena are quite opposite to each other. So what happens in semiconductors? When we are increasing the temperatures, electrons got excited and they move towards the conduction band, and that is why conductivity increases and they start conducting the electrons now. So semiconductor on increasing the temperature becomes conductor. Yeah, so this is a good note to make in mind always. So, in brief, conductors, semiconductors and insulators. Conductors have no forbidden gap, like conduction band and valence band are literally overlapped. The electrons from valence band freely enter into conduction band, and therefore very low potential difference can cause continuous flow of current. This is the semiconductor. So semiconductors have some forbidden gap between valence band and conduction band, and it is 0.7 electron volt for germanium and 1.1 electron volt for silicon. Like at 0 Kelvin, the conduction band is empty and valence band is completely filled. When we are putting a small amount of energy, the electrons can jump the forbidden gap and they can reach to the conduction band. Now the insulators have a large forbidden gap. It is very large. Generally, it is more than 3 electron volt. And there is no electron available for conduction. So the large amount of energy is needed to move electrons from valence band to conduction band. What is valence band? Valence band is a band occupied by the outermost electrons. What is conduction band? Conduction band is lowest band with unoccupied states. And what is a conductor? Valence band partially filled like copper, or conduction band overlaps the valence band. Now you guys know all these things. Look at these pictures. This is the key. If it is pure white, like there is nothing, then it is a forbidden band gap. And if they are like this in the gray shade, there are allowed and empty states. And if it is in blue, then allowed and occupied. Now look at this figure number A. It is a conductor. Why? Because we can see allowed or occupied plus empty bands are overlapping each other. Yeah, it is an insulator. Why? Because there is a large energy gap between allowed and occupied band to the allowed and empty band. This is the conductor. Again, you can see there is no energy gap, and this is semiconductor because there is very less energy gap in between. So now you guys know the basics. So what the band theory says and where we use it. Band theory helps us understand what makes a conductor, insulator or semiconductor. Good conductors like copper can be understood using the free electron. It is also possible to make a conductor using a material with its highest band field, in which case no electron in that band can be considered free. if this filled band overlaps with the next higher band, however, so that effectively there is no gap between these two bands, then an applied electric field can make an electron from the filled band jump to the higher level. Now, an important definition, semimetals. What are semimetals? These are not metals, these are not semiconductors. So, there are some electrons who can jump to the higher level, to the conduction band in some material, but they are not conducting electrons because there is some uh, band gap in these types of materials. They are semi-metals because they have some slightly higher resistance from normal metals. Okay, so yes, to note out this thing also. Now, what are valence band and conduction band? You know the definitions. Smaller energy gaps create semiconductors. So, for energy gap smaller than about 1 electron volt, the point to note out, if the energy gap is smaller than 1 electron volt, then only it should be a semiconductor. It is possible for enough electrons to be excited thermally into the conduction band so that an applied electric field can produce a modest current. The result is a semiconductor. Now, let's make some visualization of this band theory. Useful way to visualize the difference between conductors, insulators and semiconductors is to plot the available energies for electrons in the material instead of having discrete energies as in the case of free electrons, and the available energy states from bands. So this is the total energy Ek approximately equal to h cut square k square over 2m plus V. Okay, so this V fraction, the potential energy fraction, if we want to approximate this energy, then the potential energy fraction we can smear out. It will be approximately equal to h cut square k square over 2m star, where m star is effective mass. Okay, so basically the electronic properties are based on the energy band models for solids. Look at this picture. This is your valence band at T equals to 0 Kelvin. It is completely filled. It is black now. It is completely filled with electrons. Okay, there is some energy gap. Okay, this is called band gap. This is the energy difference between valence band and conduction band. This is also called forbidden gap. Now, the next band is with higher energy. It is conduction band. It may be empty in case of insulators. It may be partially filled in case of conductors. Or if there is overlapping between these two bands, that will be a conductor. So this is the energy band model for solids. Now, these are the schematic diagrams for insulators, semiconductors and conductors. You can see here the Fermi level. We'll talk about Fermi level very thoroughly in our next lecture. So all about Fermi level, if you want to know, you guys will have to see the next lecture. Part 2 will come soon. So there is large energy gap between insulator. The energy gap is less than 1 electron volt for semiconductors, and there is no energy gap between valence band and conduction band for conductors. Now let's understand them one by one. Most solid substances are insulated, and those are insulators. And in terms of band theory of solids, this implies that there is a large forbidden gap between energies of valence electron and the energy at which the electrons can move freely through the material, that is conduction band. You can see the diagram. Moving ahead, conductor energy bands. So in terms of band theory of solids, metal are unique as good conductors of electricity. Why this? Because the valence electrons can move to the conduction band, and they are basically free to move because there is an overlap region between valence band and conduction band. Semiconductor. A semiconductor material is one whose electrical properties lie in between those of insulators and good conductors, and examples are germanium and silicon. So in terms of energy bands, semiconductors can be defined as those materials which have almost an empty conduction band and almost filled valence band with a very narrow energy gap. Very narrow energy gap again is the order of 1 electron volt. Now, please keep these things in your mind. I am telling again and again. These are the types of semiconductors. Two types basically, intrinsic and extrinsic. Intrinsic means a pure type of semiconductor. Extrinsic means impure type of semiconductors. And again, extrinsic semiconductors are of two types, N type and P type. So what are intrinsic semiconductors? Those are intrinsic semiconductors which is made of semiconductor material in its extremely pure form. For example, germanium and silicon. If we'll talk about pure germanium, it has the energy gap 0.72 electron volt. And if we talk about silicon, it has the energy gap 1.1 electron volt respectively. Like approximately nearby 1 electron volt, they both having their energy gaps values. And these energy gaps are so small that even at ordinary room temperature, there are many electrons which possess sufficient energy to jump across the small energy gap between the valence and conduction bands here, from here to here, because this gap is too small. Alternatively, an intrinsic semiconductor may be defined as one in which the number of conduction electrons is equal to the number of holes. Like if we have 5 electrons, there should always be 5 holes, then that is a pure or intrinsic semiconductor. Okay. So, moving ahead, what are extrinsic semiconductor? If we are making or doping or mixing some impurities into pure semiconductors, into intrinsic semiconductors, then we are getting extrinsic semiconductors. Okay, so if we have pure semiconductor, then why we need extrinsic semiconductors? This question must come in your minds. Let me answer first. Pure semiconductors have the uncontrolled conductivity. We want to tune the properties. We want to make use of these semiconductors in our daily life. We want to use them in applications. That is why we dope some external material and make them extrinsic semiconductors, and we may increase conductivity by doing this. Okay. So, and we can tune many other properties by doping some material. Basically, semiconductors of extrinsic type again subdivided into two classes, N type and P type. What are N type semiconductors? You guys have studied about the periodic table. You know the third group elements, fourth group elements, fifth group elements, etc. Do you guys know of periodic table in which group does the semiconductors belong? They belong to the fourth group. Semiconductors are belong to the fourth group. So, if we are making some or we are mixing some impurity of fifth group into the semiconductors, pure semiconductors, like small amount of pentavalent donor atoms, for example phosphorus and arsenic, then we are getting N types of semiconductors. Why N types of semiconductors? Because we will get one free electron, one extra electron to move, and the charge on electron is negative. So this is N type. This is my trick to learn N for negative. So N type semiconductor in which there is extra electron free to move. So how we are getting an extra electron? Look at this picture. Plus 4, plus 4, plus 4, plus 4 belongs to the semiconductors. Plus 4 having the 4 electrons in their outer shell like carbon, silicon and germanium. Okay. And this plus 5 is pentavalent donor atom. For example, let's take phosphorus. Okay, phosphorus have 5 electron in its outermost shell. Now, this one electron will make bond of this one electron, one here, one here, one here. There are 4 pairing, but it has 5 electrons. But it can pair only by 4 because semiconductors have only 4 free electrons. So one electron is extra and that is free to move and that is eligible for conduction and it can move to the conduction band. Okay. Again, let's talk about p-type semiconductor. When we dope or mix some amount of trivalent acceptor atoms like boron, aluminium, etc. These are third group of elements having in periodic table. They place themselves into third group. So when we are adding boron and aluminium, then we are getting p-type. Why p-type? P-type because P for positive, the trick to remember again, P for positive and we will get an extra vacancy or hole to move. Hole is positive, that is why they are called p-type semiconductor. This is only a trick to remember. Positive from p-type to positive, positive means hole. Look at this picture. There are some semiconductors plus 4, plus 4, plus 4 having valency plus 4 and we are doping trivalent acceptor atoms. So 1, 1, 1, 3. 3 pairing it will make, but the fourth valency of semiconductor it will pair out with its hole. So there is a hole or vacancy. Okay. And this hole is free to move and it contributes in conduction. So it is p-type semiconductor. Now let's compare these. These are intrinsic semiconductors. There is no external material. They are all semiconducting materials having the valencies plus 4. This is N-type. Because there is an extra electron free to move, we are doping pentavalent atom here. This is p-type, an extra hole to move because we are doping a trivalent acceptor atom here. Now, I think the concept is clear. Moving ahead, this is the comparison between p and n-type semiconductors. So the first one for n-type semiconductor is doped with pentavalent atoms. Electrons are majority charge carriers and holes are minority charge carriers because there are number of electrons more. P-type semiconductor doped with trivalent atoms. Holes are majority charge carriers and electrons are minority charge carrier. Yes, we know that. The second one is it gives out electrons, hence known as donor atoms. It accepts electrons, hence known as acceptor atoms. Third one is the example of n-type semiconductor is bismuth, antimony, arsenic and phosphorus are the elements used for doping. We can dope bismuth, antimony, arsenic and phosphorus in the semiconducting materials in intrinsic semiconductors to make n types of semiconductor. Now to make p types of semiconductor, aluminium, gallium, indium and borons are being doped. So this is the basic comparison of p and n type semiconductors. Now let's talk about the application of these p and n type semiconductors. p-n junctions or diodes are made using these p and n types of semiconductors. We'll study the concept of diode and its working in the electronics, but for basic knowledge, if P and N both types of semiconductors are combined and made a device, then it is called a p-n junction. The schematic representation, the representation of p-n junction is this one and it looks like this one. This is your p type, this is your n type, and this is your p type, and they are both mixed, and there is a p-n junction between this. The majority of charge carriers beside these walls both sides, and this majority is good for the various applications. So how to construct and how it works, this is not, of course, this is for basic, like I have put here, but we'll study thoroughly again about p-n junction diode. So basically these are all semiconductor energy bands, and we'll talk about Fermi levels in our next lectures, and we know about the band gap. Now, so there are two cases, direct gap or indirect gap. I'll tell you about this also in my next lecture. So part 2 is coming soon. So guys, there is a Facebook page of mine called part-2 Learning. Search it out, and please add your friends too. You can message me on Telegram if you guys have any query. The group name is Physics for All. I will embed the link in the description box, so from where you can directly join to this group. And this is my mail ID, knup3640@gmail.com. You can mail me too. So I hope you guys like this lecture of today. So thank you for watching. Keep sharing, keep studies. Bye bye.